Hello everyone. In this video we are going to see how we can combine the observer and the full state feedback that we already have designed with each other indeed, and how to have a complete full state feedback controller with the observer. Here we have the state variable compensator, what we call it, and it's constructed by appropriately connecting the full state feedback control law. For the full state feedback control law, if you remember, we had u equal to minus k times x. And we connected properly to the observer. And for the observer, we have already the block diagram. So here we have the observer, which gives us x hat as an estimate of the x. And then in the feedback control law, instead of having u equal to minus k times x, we will use u equal to minus k times x hat, because its hat is a good estimate of x, so we can replace them with each other. And as a result, we will have the complete state variable compensator using the observer, as you can see here. So in the upper part, we have the system itself, which receives input. And then the input comes from the control law, multiplying x hat with the minus k, the state control gain indeed. And then at the lower part, we have the observer, and we know the details regarding the observer from the previous video. So our strategy was to design the state feedback control law as u equal to minus kx, as I just mentioned, and we assumed that we had access to the complete state x. Then we designed the observer to provide an estimate of the state x hat. And now it seems again reasonable that we can employ the state estimate x hat in the feedback control law in place of x. So we will have u equal to minus k times x hat. In this case, we won't need indeed to measure the x, the states, and feed them back to our system, but we'll use the estimate of the x. The feedback gain matrix K was designed to guarantee the stability of the closed loop system. So we needed to have the roots of this characteristics equation, which is the characteristics equation for the closed loop system. Indeed, it kind of gives the closed loop pose of the system. We needed to have the roots of this characteristics equation being on the left half plane and being in location such that we get a proper, let's say, performance for the system, for the closed loop system. Under the assumptions that we made, that the complete state x is available for feedback, the feedback control law with properly designed gain matrix K leads to desired results, that x goes towards 0 as t goes towards infinity for any initial condition x at t0. Now we need to verify that when we use the feedback control law for observed states instead of the states themselves, x hats, we retain the stability of the closed loop system. If we consider the observer again, we have x hat dot equal to a times x hat plus b times u plus l times y minus c x hat. And now we replace u with minus k times x hat. And therefore we will get x hat dot equal to a minus bk minus lc times x hat plus l times y. And u is again equal to minus k times x hat. Now if you consider this system over here, it kind of is a system with y as the input and x hat and u as the output. And x hat is the state variable here. If we calculate the estimation error, we will have E dot equal to x dot minus x hat dot. This is the error that we have for the estimate of the states. And then we replace x dot with ax plus bu and x hat dot with its equivalent ax hat minus bu minus ly plus lc times x hat. It's indeed minus x hat dot, which you can get it from here. So we have the expression here. We just replace them over here. And then we will have E dot will be equal to A minus LC times E. Because some terms will cancel here. So we will get AX minus AX hat will give us A times E. BU will cancel. Minus Y is equal to C times X. So we will have minus L times C times X hat times X indeed minus X hat, because we have the negative sign outside already. So times X minus X hat, which is in again E, and therefore E dot will be equal to A minus LC times E. And if you remember, this is exactly the same result that we got for the observer itself, yeah, when we were calculating the error for the estimation error for the observer. We also know that the underlying system model is given as x dot equal to ax plus bu and y equal to cx. Now, if we substitute the feedback law by u equal to minus k times x hat, we will get x dot equal to ax minus bk times x hat. And we also know that x hat could be written as x minus error, because we know that error is equal to x minus x hat, and therefore x hat will be equal to x minus e. If we replace this into the equation here, we will get x dot equal to a minus bk times x plus bk times the error. We also have the expression for E dot. We know that E dot is equal to A minus LC times E. Now we can put these two in the together indeed, and we obtain the matrix of the equations. X dot and E dot will be equal to A minus BK, BK 0, A minus LC times X and E. So this is indeed a system in the state space representation form. Here we can say that we have, for example, instead of x and e, we can use another variable like omega dot, and here we have omega. We can say that omega dot is equal to a star times omega, which is a system in the state space representation indeed. Yeah. On the other hand, our goal is to verify that with u equal to minus k times x hat, meaning that we are using this estimate of the states instead of the states themselves, we retain the stability of the closed-loop system and also the observer at the same time. Yeah. Now, if we find the characteristics equation for this system, the characteristics equation will be equal to determinant of lambda I minus a star equal to 0. And determinant of lambda I minus a star could be divided into these two determinants. Determinants of lambda I minus a minus bk and determinant of lambda I minus a minus lc, because we have this 0 over here. So indeed we have the matrix in the block forms. And this means that if the roots of the first determinant lie in the left half plane, and if the roots of the second determinant that we have here also lie in the left half plane, then the overall system will be stable. The overall system, including the full state feedback and the observer, will become stable. And therefore, we can employ the strategy of using the state estimates for the feedback instead of the states themselves directly. And this strategy is going to work. And over here you can also see that finding the values for K and the values for L, the state gain matrix and the observer gain, are kind of independent from each other. Yeah, so you can design the full state feedback, you can design the observer and then combine them with each other, and you can do these independently than each other, and this is called as the separation principle. It means that you can do any of them separately, and if both of them yield to a stable system, the overall system will become stable. Now here we have the design procedure summarized. We can start by determining the K, the state feedback gain, such that the determinant that we have for designing the controller has roots in the left half plane first, because we want to have our system stable, and also we place the pose appropriately to meet the closed loop control system's specifications. You can refer to, for example, the rise time for the step response, settling time, overshoot, and so on and so forth. In it, we determine the proper place for the closed loop pose of the system. Now, the ability to place the pose arbitrarily in the complex plane is guaranteed if the system is completely controllable. So this is something to keep in mind all the time. If the system is completely controllable, then we will be able to design the controller in order to place all the pose at the desired locations. Of course, for the complex pose, we will have them in the form of pairs. That's something also to keep in mind. Once we are done with that, we determine L, the observer gain, such that the determinant, the characteristic equation that we have for the observer indeed, has roots in the left half plane first of all, and also we place the pose to achieve acceptable observer performance. We try to have the error signal that we have for the observer going quickly towards 0. And again, the ability to place the pose arbitrarily in the complex plane will be guaranteed if the system is completely observable. Okay, if the system is observable, if the observability matrix is full rank, then we will be able to design the observer in order to place the pose of the observer at the desired locations. And once we are done with those two, we just connect the observer to the full state feedback law using this equation. U will be equal to minus K times X hat. And once we do that, we will be done with designing the controller in the state space domain. Okay, so I think that's all for this video. Over here we have learned how to design the controller and the observer together and then connect them to each other. In the next video, we'll talk about the steady state error. Thank you for watching and see you in the next video later.